It goes without saying that proofs by contradiction is one of the trickiest types of proofs. You start with something and then you state the complete opposite of that, and then by developing the proof you get to a contradiction, which shows us that, well, actually the initial statement was actually correct. There's a process when going through all of these proofs by contradiction exercises, and we're going to talk about it right now. And also at the same time, we're going to go through these two exercises that you see in the screen right now. But let's first talk about the step-by-step process. Let's first develop the recipe. The recipe starts with you writing the proposition, which means what you're trying to prove. And this can be proof that log of 3 base 2 is an irrational number, or it can be proof that there are infinitely many prime numbers. It can be many things, but it's important that you write P first so that in the conclusion, which is the fifth step, you can just say, hence P is true. And you don't have to write P again. And you might ask, hey, if it's the same thing for me to write P in the beginning and in the end, why would I do that in the beginning of the exercise? Well, the reason for that is it will be more clear to you what P is. That's one of the reasons. But also when you reference P towards the end, or when you write not P, for example, the examiner knows exactly where you're trying to state. You've written P, now you're going to write not P. So everything is clear, everything is much more organized. So let me mention a couple of examples. P can be log 3 base 2 is an irrational number, and the exercise in this case would say something like proof by contradiction, log 3 base 2 is an irrational number. Or P could be, for example, if n squared is a multiple of k, then n is also a multiple of k, which by the way is a very interesting proof. Step number 2, you're going to assume the negation of P is true. And careful with what you call negation, careful on how you negate a statement. So let me use one example which sounds silly, but it's actually not as simple as it looks. The negation of all cats are black, for example, is not no cat is black, for example. In that case, the negation is not all cats are black, or there exists at least one cat which is not black. Another negation that usually produces some sort of confusion is when you have if-then statements. So for example, the negation of if a student studies, then he performs well in an exam. The negation of that is a student studies or studied and did not perform well in the exam, or does not perform well in an exam. We're going to talk about if-then clauses in another video. Using the first example here, not P, and I mean this one right here, not P is log 3 base 2 is not an irrational number, or you could write in this case is a rational number. Step number 3, develop the proof. What does developing the proof mean? By using the assumption not P along with algebraic process or facts or axioms, you're going to derive further logical conclusions, and then you will eventually reach a contradiction. And that part, when you reach the contradiction, composes step number 4. You need to identify the contradiction. Whenever you get the contradiction or to a contradictory statement, you will write which is a contradiction. You need to make it very clear to the examiner that you know when that happened, when you reached the contradiction. And then we have number 5, which is the conclusion. We are going to write the conclusion. And writing the conclusion in a proof by contradiction is not as long as writing the conclusion in an induction proof. In this case, you're just going to complement step number 4 with the following. ... Therefore, by contradiction, P, whatever P is true. And there you go. And this is why it was helpful to define what P is in the beginning of the proof. Now let's go through the 2 exercises and apply that recipe. Exercise number 1. Prove by contradiction that if n squared is odd, then n must be odd as well. Now we have right here an if-then statement. And remember that we're going to talk more about this later, but the negation of if R, then S is R and not s. I didn't use p and q here because I want to use p for the actual proposition, but the idea is the negation of if something then something else is something and not something else. So something does happen, but something else ends up not happening. Now let's follow the step-by-step process. Number one, we're going to write the proposition. What are we trying to prove? We're trying to prove that if n squared is odd, then n must be odd. And in step number two, we're going to assume the opposite. We're going to negate p, which means that we're going to assume there exists an integer n such that n squared is odd and n is even. So we're going to assume that n is actually even. And we're going to arrive, of course, to a contradiction. We're going to get a contradiction. We represent even numbers as 2 times k, for example, or 2 times w, or 2 times anything, k being an integer. Therefore, n squared is 2k squared, which is 4k squared, which is 2 times 2k squared, which is even. Do notice that in the beginning, we assumed that n squared was odd. So this is a contradiction. So the fact that n squared is an even number is a contradiction. Therefore, by contradiction, p, the proposition, is true. Now let's move to exercise number 2. We're going to prove by contradiction that there are no positive integers p and q such that 4p squared minus q squared is equal to 25. We're talking about integers. So keep that in mind. Let's start with number 1, which is to define the proposition. So p is, there are no positive integers p and q such that 4p squared minus q squared is equal to 25. We're going to assume not p, which by the way, you can write like this as well, or simply not p. So you can write not p in one of these 3 ways. Just select one and you can use that one. What is not p? It's important to state what not p is. Not p in this case is there are, or there exists, which is a little bit better, integers p and q such that 4p squared minus q squared is equal to 25. Now, if this is the case, we are going to work on this equation a little bit more. Let's factor out the left-hand side. We have a difference of 2 squares. This is the same as 2p squared, and this is only q, of course, squared, which means that we can rewrite the left-hand side as 2p plus q times 2p minus q. And the right-hand side is 25. And by the way, you want to explain every step that you're taking. So for example, what we can do here is, given that we have a product which is 25, either we have 5 times 5, or 25 times 1, or 1 times 25. We're going to consider these 3 cases, knowing that, as I mentioned, the prime factorization of 25 is 5 times 5. So given that the product between 2p plus q and 2p minus q is 25, and both 2p plus q and 2p minus q are integers, we have 1 out of 3 possible scenarios. You can call these cases 1, 2, and 3, or 3 possible cases as well. What is case number 1? Both 2p plus q and 2p minus q, they're equal to 5, which means that the product will be 25. Theoretically, it sounds all right. However, if this is the case, by adding the 2 equations, we get 4p equal to 10, which means that p is 5 over 2, which is not an integer, which is a contradiction. Remember that in the beginning of the proof, we assumed that p and q were integers. Now let's tackle case number 2. In case number 2, we have 2p plus q equal to 25 and 2p minus q equal to 1. Do notice that 25 times 1 will lead to 25 as a result. Sounds reasonable, but let's see if it's actually reasonable. Now we have, when we add these 2 equations, for p equal to 26, which means that p is 13 over 2, which is not an integer. Now over here we have a contradiction as well. And the third case, as you might imagine already, will not work. In this case, we have 2p plus q equal to 1 and 2p minus q equal to 25. When we add these, we also get p equal to 13 over 2, which is not an integer. So we have a contradiction as well. Now, given that none of the three cases or scenarios are valid, by contradiction, we can state that p is true. Now that is it. How to ace proofs by contradiction in 5 steps with 2 examples fully solved. I'll see you on the next one.